Good morning. What day is it? It's Thursday. All right. 5/28/20. Learning targets today. Hey, we're going to go from our discussion of fresh water on the earth to now some of the salt water on the earth, which of course you remember is about 97.5% of all the water on the earth. So what do I want from you? I can list and describe several ways in which the oceans are critically important. So this is what I normally would have called Unit 10. We're only going to get just a touch of it, but it's good stuff. Okay, so I think this comes from one of my last years of classes where we just did a little brainstorming. And if I remember right, I think I just said, all right, open up your Chromebooks, everybody take, 3 minutes here and find some reasons why the ocean's important. And this was just kind of a list they came up with. They said 76% of U.S. trade travels on the oceans. You ever see pictures of those super freighters piled with shipping crates? Hundreds of shipping crates, maybe thousands of shipping crates on those things. Shipping materials by airplane is tremendously expensive. So most of the trade that we do with other countries, now of course, we can trade with Canada by road, we can trade with Mexico by road, but if we want to trade with Europe, if we want to trade with Asia, that stuff travels on ships. It says that the ocean's important for food. About 16% of animal protein, fish, other types of seafood, lobsters, clams, mollusks, octopus, squid. That's protein coming from 16% is quite a lot. The oceans produce about 50% of the oxygen for the planet. And this comes from the little algae and plants in the ocean. So as much as our trees and everything else are important to us, the oceans produce a very large part of the oxygen that we need. The oceans absorb some of the CO2 that we put out into the planet. The ocean's important for medical ingredients, recreation, boating, swimming, fishing, scuba diving. And oceans are important to regulate the climate. We're going to hit on that one quite a bit. All right, so that was just a brainstorm list. Let's get into it a little bit. Hey, how many oceans are there? What can you name? Did you come up with the Atlantic? Did you come up with the Pacific? Did you come up with the Indian Ocean? How about the Arctic Ocean? How about the Southern Ocean? I'm up to 5. But honestly, aren't they all connected? I mean, if you look at a globe, I can see one over sitting on a desk right now. I can see right now on that globe, I can see the Indian Ocean and I can see part of the Pacific Ocean, and I see water connecting in between the two. Literally, I guess if you were a good enough swimmer, you could swim from the Indian Ocean to the Pacific. You could swim from the Pacific around South America into the Atlantic. While you're doing that, you're probably dipping into what's called the Southern Ocean. That's the one I really don't understand, is the Southern Ocean, because basically they just draw a ring around Antarctica and call that an ocean. At least the other ones, Atlantic, Pacific, it's kind of outlined by some land. So how many oceans are there? Really, it's debatable. Depending on, what you read, you'll usually see anywhere from 1 to 5. I tend to think of it as the oceans. They're all connected. But we name different parts, different things, okay? They are all connected, the oceans. All right, let's get into significance. The first thing I want to look at, the oceans moderate temperature and weather. Temperature and weather, the average of temperature and weather could be called climate. So, if you just to get into what is the difference between weather and climate. When I look outside my window right now today, it's raining, and it's fairly warm. We could put a measurement to it. It's probably, I think, about 70 degrees, maybe a little under 70 degrees Fahrenheit right now, and it's cloudy and raining. That is the current weather. Now, if we take the average of what happens here in Edgar, Wisconsin over a long period of time, it's not rainy and cloudy every day. The average of that is what we describe as the climate of an area. Okay, so the weather is what's happening right now. The climate is the average weather. All right, so I've got a map kind of focused on the Atlantic basin. We even within the Atlantic, we talk about the North Atlantic and the South Atlantic. And you can see North America, South America, Africa, Europe. Now, the equator runs right through here. And you know that the sun shines more strongly or more directly on the equator. So this part of the Earth tends to get a lot of sunshine. And of course that's energy. And so what happens here is, it gets hot, yeah. But think about all this water. When you put energy on water, the water evaporates, right? And if we think back to previous chapters, we know that evaporation absorbs energy. So evaporation that's an endothermic process. The energy goes into separating the water molecules from each other. And so what happens is, if that's absorbing the energy, it keeps the overall temperature cooler than it would otherwise be. So while it gets very hot, there's some areas over here that daytime highs, 120 degrees is not unusual. It gets very hot. But without all this water out here, it would get even hotter. Okay? And where you get the most extreme temperatures is where you're away from the water. So if you're closer to the water, it tends to moderate temperatures. So evaporation absorbs energy. That keeps things cooler than it might get. All right, that's not the greatest sentence in the world, but I'm saying, if it weren't for the evaporation, it would get even hotter yet. Okay, well, let's see, what else is going on? Hey, the very north regions and the very south regions of our planet don't get as much direct sunlight. And so what tends to happen there is, when it's not getting as much energy, the temperatures are cold, right? So this was hot. This is cold. And what happens to water when it gets cold? Well, water freezes. I don't know why I'm writing freezing with the K. Okay, water freezes. So freezing, in order to freeze water, you have to get the energy out of the water. So freezing actually releases energy. Freezing actually releases energy. The energy comes out of the water. And so that's going to keep things warmer than they might be. And again, poor sentence, sorry. But what I'm trying to say is that without the water there, it would get even colder. Okay, so yes, it's hot here, but without the water, it would be hotter. It's cold here, but without the water, it would be colder. All right, we can repeat that down here. And there's one more big factor, and that is, so much of our Earth is covered in water, and there are currents that stir the water due to the motions of the Earth. And there are some major currents, like here in the Atlantic, there's a current that flows across the equator, comes up past the United States, and it flows this way, and then there's another current that comes around this way. And so what that does is kind of stirs the water. So it's not just that this water keeps getting hotter and hotter and hotter and evaporates away, and it's not that this water just keeps freezing. Some of this warm water is flowed towards the north, and some of the cold water flows towards the south, and that kind of balances the temperature over the planet some. So currents move heat around. In the South Atlantic, we have currents like this. So, yeah, overall, this is really tremendously important. If you look at Edgar, Wisconsin, right about in there, maybe there, and then you think about Europe, we have foreign exchange students who've been coming from various parts of Europe, but you say somebody's coming from Northern Europe, they're actually further north than we are. And yet most of those students have not experienced winters like we normally get. We've had some Norwegian students, they've experienced some winter. But students from Denmark, Germany, France, they're further north than we are here in Wisconsin, and yet they get a little bit of snow and then it melts, and they don't get a lot of prolonged cold weather and things like that. And that's all because this current comes right over from, starts down here at the equator and wraps up towards Northern Europe, and it brings warm water with it. Warmer water. Okay, that doesn't mean that if you go swimming out here that the water is balmy and toasty warm, but it's warmer than it otherwise would be. All right, it's a really important thing, but I think I've been beating it enough, so I'm going to go on. This was just an older version of that same thing, okay, showing lots of sunshine hitting here, water warms up, evaporates, keeps things cooler than normal. Up here, water freezing, keeps it warmer than normal. Currents stir it around. Okay, what else? Oh, here's a map of some of those ocean currents, and you can see here's the Atlantic, and we tend to get this warm current. This is called the Gulf Stream. You've heard that. If you've ever watched Finding Nemo, this is probably what's called the East Australian Current. The EAC, dude. Oh, that was terrible. Okay, but we have these giant currents. You see how in these big bodies of water they turn like that? That's called a gyre. So we have the North Pacific Gyre, we have the South Pacific Gyre, the North Atlantic Gyre, the South Atlantic Gyre. There's gyres in the Indian Ocean, these giant circular patterns. All right, let's get back to significance of the oceans. Hey, the ocean's like a giant solar collector. So a lot of the energy coming from the sun gets absorbed by the ocean, and we can possibly tap into that as an energy source. Biologically rich. Okay. Bio means living. There is a huge amount of plant and animal life in the ocean. There's a word in science called biomass, and that's the mass of all living things in a region. And there is a lot of biomass in the ocean. A huge number of people on our earth depend on the ocean for food and their living. Not only their food, but they catch food for others. Tremendously important, okay? The food chain. And the food chain in the ocean starts out with these little tiny, nearly microscopic organisms. Think about the water cycle. We talked about that a bit in the last chapter. In order for us to have rain, you first have to evaporate something, right? Well, 2/3 of the ocean of the world is covered in water, the oceans mostly, and that's where most of the evaporation happens. So our rain out here today in Edgar, Wisconsin, very possibly is a result of evaporation off of oceans. Trade and transportation. Okay, we said that the number, and I didn't verify this number, but it said 76% of our foreign trade arrives on the ocean. Transportation, they just were replaying the movie Titanic on TV the other night. That's maybe not a great example of transportation, but 100 years ago, if you wanted to go to somewhere else in the world, that was your most likely bet, was to get on a boat to go somewhere. Airplanes, weren't really that at that point yet. Over half of the oxygen in our atmosphere, the stuff that we're breathing, is produced from plants and algae in the ocean. That's huge. In return, the waste gas that we're breathing out, and by the way, there's always a misunderstanding, I think. Some people think that we breathe in oxygen and we breathe out carbon dioxide. When you exhale, you're exhaling mostly the same stuff that you inhale, with slightly less oxygen and slightly more carbon dioxide. It's not, because if we were using up all the oxygen that we took in every breath, there wouldn't be enough oxygen to go around. All right. I'll just go into this just a little bit. What is the ocean made of? Well, first and foremost, it's water, right? But we know that it's not just fresh water. It's got salts in it. Now, I use the word salts plural because from a chemistry standpoint, salts just refer to a whole variety of ionic compounds. And so some of those salts could be sodium chloride, could be magnesium chloride, could be calcium chloride. And if you just listen to those names, you heard chloride, chloride, chloride. So actually, after the water, the most common atom in the ocean is chlorine. Then comes sodium, because the sodium chloride would be the most common salt. But we're going to have other things like magnesium and calcium, and there's going to be some sulfur in the ocean. There's going to be all sorts of things in the ocean. Get this, there's many tons of gold in the ocean. Problem is that it's so spread out, it's not at all practical for us to try to get it up. There's all sorts of stuff dissolved in the ocean, okay? But we think of salt water, and the primary salts would be sodium chloride. Wasn't going to do that. I did want to hit the word Salinity is the amount of salts dissolved in the water. Okay? And let me give you a little bit here. Because we have all that evaporation happening at the equator, when you evaporate, you're taking the water out, but you're leaving the salts behind. So the more evaporation you get, the higher the salinity tends to get. Okay? So oceans tend to be saltier near the equator. And if you have less evaporation, like up by the poles, well, then the salt stays around. And then let's say you do have some, summer in the north, and some of that ice melts. Well, the ice is primarily fresh water, so when that melts, you're lowering the salinity. So we tend to have differences in salinity in different parts of the ocean. And I think, the last thing that I just wanted to talk about as a science term is density. Density is mass over volume. And so in our oceans, we have some parts are warmer, some parts are colder. And so let's just kind of highlight, don't worry about all this, but let's highlight this right here. If the water gets warmer, it becomes less dense. So therefore, if water becomes colder, it becomes more dense. And the more salt you dissolve in water, the more dense it becomes. This is important because it affects how water circulates. All right, I'm going to ask you a few questions based on today's video. See you tomorrow.